Okay, let's continue now with the application of the MPL method to dynamic discrete choice games. In a second paper with Pedro Mira, we propose the extension of these ideas to the case of dynamic discrete choice games with incomplete information. Then let me start providing some general features of the type of models of dynamic discrete choice games that we consider. That is a relatively straightforward extension of the single agent models to the case of games. And basically we got the idea of this extension from a paper by John. In fact, from a couple of pages at the end of a paper by John in the Econometric Society conference of 1990, something like that, where he says, okay, this can be extended to games, and it can be convenient in this context to consider games of incomplete information and things like that. And these two pages were gold for us, though I have the impression that very few people in the literature know these two papers, these 2 pages in John's paper, but they are basically most of what the dynamic discrete choice games that we use in the literature of dynamic structural I/O these days, they build in those 2 pages. Okay, then let me provide some description of these models. Again, time is discrete and indexed by t. Now we have m players. I will be talking about players and firms as synonymous. And I will use the index I to index players. Then every period t and a player takes an action, y, to maximize the expected and discounted flow of payoffs. Again, a stationary environment, infinite horizon, payoff functions, and transition probabilities of the state variables that do not change over time, okay? The payoff function, now we have a game. What does it mean? Basically, well, that now the payoff of a player player I at period t. Now it depends on his own actions, but also the vector of the actions of the other players, okay? That I'm going to use, describe using this minus I index, okay? In this literature, following the seminal papers by Maskin and Tirol, and later by Erickson and Paker's paper that has been very influential in empirical I/O, in dynamics empirical I/O models, we use the concept of Markov perfect equilibrium, okay? Then the concept of Markov perfect equilibrium, the key restriction or the key condition that it imposes is that the players at every period, they use strategy functions that depend only on variables that are payoff relevant at that period. That is, they are variables that they are affecting the profits, their own profits, or the profits of other firms at period t, or that help to predict the profits, their own profits, or the future profits of other firms in the market. Either they affect today's profit or future profit. Okay, but they are not going to condition on state variables that they are not payoff relevant. Okay, and this is a key condition of the Markov perfect equilibrium. There are different reasons why we use this. It's very convenient because we are going to reduce the dimensionality of the state space. This is convenient for computation. This is convenient for econometrics. Okay, there is also if you want a theoretical or information-based justification of this equilibrium concept that Maskin and Tirole emphasize, of course, in their paper, in the seminal paper that proposed, is that if we consider a meta game where these players could choose basically how much information they use to play their strategies. They say, okay, I can condition my strategies only on today's payoff relevant, but I can condition also to some history, okay? And I can decide how much history of the previous states I can use to determine my strategy, okay? Suppose that we were considering this type of meta games where players could also choose the amount of information that they use to construct their strategies. Well, what this type of model says is that if the others players are using only payoff relevant state variables, I cannot improve my payments in equilibrium if I use additional information, okay? And in some sense, using payoff relevant only state variable is kind of an equilibrium of this meta game, okay? It will not be the case, for instance, if you use less than the payoff relevant state variable. If everybody is using not all the payoff relevant state variables, I can gain by using additional information. But if all the other people is using is only the payoff relevant state variables, my best response of this meta game is using also only, there is not any gain of using additional information. And if using additional information is costly, we can think that in some sense, this Markov perfect equilibrium is like an equilibrium of this meta game, okay? Okay, then a Markov perfect, this is the first condition, is that the player's strategies depend only on payoff relevant variables. Then let me use X, let me ignore for the moment the epsilons, xt as the vector of state variables at period t, then every player I is using a strategy that only depends on X, okay? The second condition that defines the Markov perfect equilibrium is that basically it's a Nass equilibrium condition, but in a dynamic context, okay? Taking as given the strategies of the other players, I know how the other players will behave now and in the future. Now, what I have to solve is a single agent dynamic programming problem. That is, my best response is the solution of a single agent dynamic programming problem because I've taken as given how the other firms will behave now and in the future. Okay, then the best response of a player will be the solution of this single agent dynamic programming problem. Okay, then the Markov perfect equilibrium says that everybody's strategy is the best response to the other's strategy. And best response here means the solution of a dynamic programming problem that takes the other player's strategies as given. Jasmine? We are going to see a lot. Thank you. Yes, that is going to be one of the main issues in this literature. Yeah, thank you. Though, let me say related to this, that the best response is going to be a function. Okay, taken as given the strategies of the other, the solution of the dynamic programming problem it has a unique solution. Okay, okay, and best response are still functions in this model. But of course, despite we have that best response are functions, we may have multiplicity of equilibrium. Okay. Okay, then let me use V super index alpha to represent the value function of player I, taken as given the strategies of the other players. Okay, it is the maximum value of player I can achieve in a state X taking as given whatever are the strategy functions of the other players, okay? And this can be obtained as the solution, okay? This value function is the solution, the unique solution of this dynamic programming problem described by this Bellman equation, okay? Where basically is a standard dynamic programming problem once we take into account that we define this payoff function and these transition probabilities of the state variables, okay? What this payoff function pi alpha means, well, is the payoff if I take as player I action Y and the state is X, taking into account that the actions of the other players are given by their strategies, okay? And similarly, this is the transition of the state variable as if we were in a single agent model. That is, what is the probability distribution of the vector of state variables at period t+1, given my action today, given today's state, taking into account that the other players today will behave according to their actions, okay? Then once I take the strategy functions of the other players and I construct this new indirect, if you want, payoff function and transition probabilities of the state variables, where we have solved in this payoff and in this transition the actions of my opponents, now we are in a single agent model, okay? Give me these payoffs, give me these transition probabilities, I plug in them there in the Bellman equation, and now I have a single agent model, and this is a contraction, it has a unique solution, a unique value function, a unique best response strategy function. Cool. Doesn't mean that we have a unique equilibrium, not at all. It means that we have well-defined best response strategies that are the solution, the response to the strategies of the others that solve a standard dynamic programming problem. Okay? Any question about this? Sure. There are many, yes, this is subgame perfectness equilibrium. Yeah. Markov perfect equilibrium is a particular case of subgame perfectness equilibrium. Yeah, good. Okay, then using this description of an agent dynamic programming problem as a best response, we can describe a Markov perfect equilibrium as n tuple of a strategy function such that every player is best responding by solving this dynamic programming problem that is a best response, okay? Okay, now this is the definition of a Markov perfect equilibrium in the space of actions of the players. Once we introduce incomplete information in the game, we can define this Markov perfect equilibrium in the space of choice probabilities. Okay, and suppose that we have our model, and now there are different ways in which we could incorporate this incomplete information. And let's suppose that we incorporate it following John's condition additive separability assumption by adding here these epsilons, one for each choice alternative. And let's suppose that these epsilons at period t, they are private information of player I, but they are unknown to the other players. And let's assume that these epsilon, they are IAD over time as a cross player. These are private information shocks. There's some shocks in the cost of market entry, some shocks in the cost of making a particular investment or adopting a new technology or buying a particular product in the case of consumer choices, but they are known to the own agent, but not to the others, okay? Then that means that from the point of view of a competitor or other player in the game, all what they know is the probability that you are going to take a particular action, but they don't know exactly the action that you are going to take because they don't know your private information, okay? Okay, they know that you are an incumbent in the market, you were in the market at previous period. Given that, and given that market size is relatively large, given the states of the game, they believe that it's very high probability that you will continue in the market today, that you decide to continue in the market. But they don't know that there is some epsilon in your fixed cost, okay? Some private information shock in your fixed cost that might imply that you have some probability of exit, okay? Then that is the type of game that we consider here. And then in that case, we have also similar type of definition of a Markov perfect equilibrium, but now we can describe it in terms of choice probabilities. Similarly, as we have described the solution of a dynamic programming problem in terms of choice probabilities, we can also define a Markov perfect equilibrium in terms of choice probabilities, okay? Each player has a vector of choice probabilities for each possible action and each possible state of the game. And if we are in a model of market entry and exit, then the state of the game is market characteristic, market size, input prices, things that affect the profit of everybody, and then the incumbency status of each firm, whether firm 1 is in the market at previous period, firm 2 was in the market or not, and so on, okay? And that determines the vector X, okay? And given the vector X, okay, a particular value of the vector X, we have the probability that firm 1 is in the market this period, the probability that firm 2 is in the market, and so on, okay? Or described in a different way, for each firm, for firm 1, we have a vector of probabilities of being in the market for each possible value of X, for each possible market structure and exogenous characteristics of the market, okay? Okay, then that's a description of a strategy of a firm as a vector of choice probabilities. Give me what is the state of the market, and I will tell you what is the probability that I will be active in the market or not, okay? Then similarly as in the single agent model, we can describe here an equilibrium as a vector of choice probabilities or an n-tuple of vector of choice probabilities, one for each player, such that a vector of choice probabilities of a player solves the policy iteration mapping, okay? It's a solution of the policy iteration mapping for that player, okay? That's what this expression means, okay? This is the best response of policy iteration. Remember that in the single agent model, we have an interpretation of the policy iteration mapping as a best response of an agent to himself in the future. I take as given my behavior, the vector of choice probabilities in the way that I'm going to behave in the future, that is going to give me some values for the future, and then today I best respond to myself in the future by choosing what will be the optimal choice probabilities today, taking as given myself in the future, okay? Well, here now we have a real game. In addition of this game against yourself in the future, we have also a game against the other, okay? And what this mapping means is that let's take my own behavior, the behavior of player I in the future as given. Let's take, as described by the choice probabilities, let's take the behavior of my opponents, the other players of the game as given, as described by their choice probabilities. And now I'm going to best respond. I'm going to get, using these choice probabilities, I'm going to make evaluation. I'm going to get the value of making different choices today. And that is going to give me what is my best response choice probabilities today. Okay? That what this policy iteration or best response probability mapping give us. Okay? Similarly, or equivalently, almost equivalently as before, this policy iteration mapping is the composition of two mappings. The policy evaluation takes the choice probabilities of everybody, and then we are going to construct this valuation matrix that is going to give us basically the value of the probability of visiting different states in the future, and using this matrix, we can obtain discounted values. And then a policy improvement mapping, taking these values I've given, what is my best response choice probabilities, okay? For, again, the logic, if we assume that these private information epsilons, they take this string value, type 1 string value distribution, we can get more explicit or concrete expression for this policy valuation and policy improvement operators, okay? Very similar expressions as before. What is the difference? Well, the difference is that now these transition probabilities that we have here, they depend on the actions of the other players. These F matrices, they are just matrix versions of these, okay? But also my own payoff, my vector of payoffs depends on the choice probabilities of the other players. Basically, if we go to the payoff function today, I don't know what will be the action of my competitors today. I need to integrate over the probability distribution of my competitors, and I will use the choice probabilities of the competitors. Okay. Okay, then we have this difference, okay? Both now these transition probabilities and these expected payoffs depend on the choice probabilities of the other players. Other than that, you can see that this valuation operator is very similar to the valuation operator that we had for the single agent model, okay? Similar type of interpretation. Yep.
So when beta equals 0, this would reduce to this concept of quantum response equilibrium of McKelvey and Walford?
Pretty much, yes, definitely, yes. Exactly, in the static case, this is pretty much, of course, in experimental economics, as you know, the type of justification that they have is not necessarily incomplete information. They have more type of behavioral interpretation of this quantal response. But yes, it can be seen as a dynamic version of the Palfrey-McKelvey quantal response equilibrium. Exactly. Yeah. Okay. Then the policy improvement mapping is basically the same as before, okay? Almost the same as before. I take the values, the vector of values as given. This is the vector of values of visiting each possible state, okay, in the future. And then basically I take into account that the transition probabilities of the state variables depend on the choice probabilities of my opponent, and my expected profits today also depend on the choice probabilities of my opponent, okay? But very similar to the policy iteration mapping that we had for single agent. But we have embedded the choice probabilities of the other players, both here in the expected payoffs and here in the transition probabilities of the state variables, okay? Possible solution methods. Well, one possible solution method will be policy iteration. okay, as we have seen in the single agent model. Let's start with some arbitrary vector of choice probabilities for every player, for every action and every state. Let me call it P0. And then at every iteration n, what we do is we obtain the best response of player I, of each player I, to the choice probabilities of everybody, including himself, in the previous iteration, okay? And basically, it will be going through this valuation operator, this constructing this transition matrix F for the choice probabilities, these expected payoffs, inverting this matrix, making this multiplication, plugging in this here, and then obtaining these best responses, okay? Similarly as before, what is the main computational cost of one policy iteration is inverting this matrix, okay? Typically, in the case of games, the course of dimensionality can be more severe than in single agents. The state space can be larger, okay? But that is not going to be the main issue of this policy iteration method here. The main issue, okay, then we can iterate, and then we check for convergence. What is the main difference with respect to the case of single agent? Well, the main difference is that now this policy iteration mapping is not longer a contraction in general, okay? There are many different situations, very simple, even the simpler versions of these games, models of market entry and exit, even with some homogeneous players, where we can have a multiplicity of equilibrium, okay, in these games. Then in general, this is not a contraction, okay? This algorithm does not necessarily converge as a solution algorithm. And in addition, because it's not a contraction, we can have multiple Markov perfect equilibrium, okay? Which is going to be also an issue, not only for solution, but also for the estimation of the model, okay? And multiplicity of equilibria and non-contraction of this policy iteration mapping is going to be, they are, of course, closely related issue that will be relevant for the estimation of this model, okay? And these are two important issues or challenges. And the other, of course, the course of dimensionality that in the case of games, basically with heterogeneous players, if we have a state space per player that is of dimension, let's say, x, the dimension of the state space of the game is x to the power n, where n is the number of players, okay? And even for relatively small state spaces for each individual player, we can have very easily very large state spaces once we have like 5 or 10 heterogeneous players in our game, okay? Okay. And for instance, a game of capital investment between firms or quality choice between firms, suppose that a firm's capital, the key state variables is what is the capital stock of a firm, and suppose that the capital stock is an state variable that can take only 10 values, then the single agent version of this game will have a state space with only 10 points, okay? Now we have 6 firms playing this game, and then the state space will be 10 to the power 6, okay? And easily you can see that this becomes very complicated, even for apparently very simple dynamic games, okay? Okay, then I'm going to talk again about full solution estimation methods with focus on the nested pseudo likelihood method. But I think that it's important to talk briefly about the maximum likelihood estimation of this type of model, okay? Then let's start considering what if we have a model, a dynamic game that have a unique equilibrium. And there are good number of empirical applications in I/O, for instance, papers by Igami and papers by other authors, that they have made assumptions to guarantee that we have dynamic games with that for a given vector of a structural parameter, we always have a unique equilibrium, okay? Then in that case, the estimation, the maximum likelihood estimator will be a relatively standard definition and implementation, similar to the one that we have for the single agent model, okay? We have a likelihood function with the choice probabilities and the transition probabilities of the state variables under the assumption that we have considered. Here I have changed the notation from Y to A, sorry, okay? Now A are the actions, the dependent variable, sorry. But this is a function. This is a likelihood, this is a well-defined likelihood function. That is, for every value of theta, the dynamic game has a unique equilibrium, has a unique vector of choice probabilities that are the Markov perfect equilibrium, okay? And we can use nested fixed point algorithm in this case without problem. That is going to give us the maximum likelihood estimator, okay? Okay, this is the BHHH version of the nested fixed point algorithm. What if we have multiplicity of equilibrium? Okay, the first thing that I would like to say that is still the maximum likelihood estimator is well defined and it has the standard nice properties. Okay, despite we have multiplicity of equilibrium. Okay, in the game. Okay, then again it's going to be useful. Yep. Okay, it's going to be useful to define to use the pseudo likelihood function to define the maximum likelihood estimator. Okay, as we have done in the single agent model. Okay, then again, what is the definition of the pseudo likelihood function? Similar as before. Remember when I presented the pseudo likelihood function in the single agent game, I say, okay, we can interpret this pseudo likelihood as a function, as a likelihood function in a model with two sets of parameters, the structural parameter theta and a vector of parameters p that represent the beliefs that the agent has about how he's going to behave in the future, okay? And then these choice probabilities, these psi probabilities are the best responses, the optimal behavior of an agent, given these structural parameters, and his beliefs about how he is going to behave in the future, okay? Well, now we have basically the same type of interpretation, with the only difference is that now these belief parameters, they are not only beliefs about how I'm going to behave in the future, it's also beliefs about how my competitors are going to behave now and in the future, according to their choice probabilities, okay? Then this P has a PI, my own behavior in the future, and a P minus I, the behavior of my opponents. But given this, okay, these are belief parameters and structural parameters. And this is a well-defined function, because in this model, as we have seen, best responses are functions. Equilibrium probabilities are not functions. They can be correspondence because we have multiplicity, but best responses are functions, okay? And we might try to say, okay, let's maximize this likelihood function with respect to theta and p and obtain maximum likelihood estimates of structural parameters and beliefs. Without further restrictions, of course, we don't have identification. We cannot separately identify beliefs and preferences, okay? But this is because this likelihood is not incorporating all the restrictions of the model, okay? Particular, these beliefs, according to the model that we have seen, they should be equilibrium beliefs. They should be a solution This should be a Markov perfect equilibrium. Okay. And therefore, we can define the maximum likelihood estimator as a pair of theta and p that maximizes this likelihood subject to the equilibrium constraints, as we define in the context of single agent. We can also define the single agent maximum likelihood estimator in that way. Well, exactly the same for dynamic games. Okay. And this is the definition of the maximum likelihood estimator with multiple equilibria. Is the value, basically what I'm doing now is defining the Lagrangian problem associated to this constraint optimization problem. We want to maximize this likelihood with respect to theta and p, subject to the constraint that p is a fixed point, is an equilibrium of the mapping psi, okay, given theta, okay? And this constraint maximum likelihood estimation can be described as a Lagrangian problem, okay? That's what we have here, okay? Then this is the Lagrange function, is the pseudo likelihood plus the vector of Lagrange multiplier multiplying the equilibrium restrictions, okay? This P, remember that is the vector of choice probabilities for every player and given a player for every action and every state, okay? It's a high dimension vector, okay? And for the same reason, this vector of Lagrange multiplier is a high dimension vector, okay? Then the Lagrange conditions of optimality take this form, okay? The first order conditions of optimality. Okay, let me say that this is a well-defined constraint maximum likelihood estimation under the standard regularity conditions that are satisfied in this model. This estimator is consistent, asymptotically normal, and asymptotically efficient, okay? Does it matter that we have multiplicity of equilibria? Not at all, okay? Okay, it's a model with multiplicity of equilibrium, but this is a standard constraint maximization problem, okay? Yeah. Let's enter a little bit into the details of this maximum likelihood estimator, because it's going to play a role in terms of the computational cost of implementing this estimator. Then, well, what we would do, of course, what we cannot do, okay, is the type of implementation of the nested fixed point algorithm that is going to be very costly to implement the nested fixed point algorithm in the way that we do it using single agent models, okay? What we do? What we do is we do not consider a Lagrange problem like here. What we do is that give me theta. We are searching for the maximum likelihood estimate of theta using the BHHH, for instance. We have a trial value of theta. Given that theta, let's compute an equilibrium of the model, okay? Well, the problem is that we have many equilibria, or we can have multiple equilibria of the model, okay? Then which equilibrium we choose, okay? Okay? And by using this Lagrange formulation of the maximum likelihood estimator, we are avoiding that problem, okay? You can now consider a BHHH version or Newton's implementation of the maximization of this problem. And then at each iteration, we have a value of theta, a value of p, and a value of lambda, okay? Okay, and we are going to iterate to calculate the maximum likelihood estimator, okay? Then, in other words, we can consider the Lagrange equations that satisfy the first order conditions of this maximum likelihood estimator and look for a solution of these Lagrange equations, okay? Then we have three sets of equations in the Lagrange condition. We have, yep.
allowing you to choose between the equilibrium, right? And that's what you've got a potential set of equilibria that give you different P minus psi of things. And for some of them, they're going to be quite far. And because you're minimizing this whole thing, lambda is effectively telling you the cost of choosing one equilibrium over another.
Very good question, a difficult one. I wouldn't interpret it in that way, okay? Because the different equilibria that we are going to have in this model, typically the set of what is called regular equilibria, they are isolated equilibria, okay? And they are not contiguous to each other. Then basically, these marginal conditions, they are not going to play a role in terms of choosing between the different equilibria. It's more like what is the cause of deviating from an equilibrium condition, okay? In terms of likelihood, okay? And yeah. Then we have the marginal conditions of optimality with respect to the Lagrange multiplier that are just the equilibrium conditions. We have the marginal conditions of optimality with respect to theta that they are going to enter in this derivative of the likelihood, pseudo likelihood with respect to theta, but also in the restrictions, okay? And it's lambda multiply the derivative of this, of the Jacobian of the Polish iteration mapping with respect to theta. And then we have this additional vector of first order conditions of optimality that is super high dimension, okay? Because it's the derivatives with respect to the vector of choice probabilities. And then this is the derivative of Q with respect to P plus lambda multiplying the derivative of this with respect to P. And there is a typo here. This would be the identity matrix minus this Jacobian matrix, okay? Okay, let me relate these conditions. Yes? No?
Do you have other conditions ensuring that the class of equilibria is countable with finite versus
excellent question. Yes, okay, that's what I mentioned it's possible to show. There is a paper by Uli Doroselsky and Satterwhite in quantitative economics, in theoretical economics, sorry, where they show that they characterize the set of Markov perfect equilibrium in this model. And they saw that the set of regular equilibria is finite, discrete and finite. Yeah. And basically what that means is that the set of regular equilibria, they are basically equilibria where this Jacobian matrix is not zero, okay? If this Jacobian matrix is zero evaluated at the equilibrium, okay, then we have a non-regular equilibrium, and that means that we can have a continuous, okay? But if that is not the case, okay, or if we ignore that type of equilibrium, the set of equilibria where this Jacobian matrix is not zero is finite. Yep. Okay. Okay. Okay, let me relate this expression to the NPL estimation to single agent. And let me, looking at this expression, explain why the NPL estimator with single agent is exactly equal to the maximum likelihood estimator, or the estimator that satisfies the two conditions of NPL estimation for single agent is also an estimator that satisfies the likelihood equations, okay? Or the Lagrange conditions for constraint maximum likelihood estimation. Remember that which were the conditions that define the NPL estimator in single agents? Is given P, okay, for given P, theta maximizes the pseudo likelihood in terms of local conditions. That means that this derivatives, vector of derivatives, is equals to 0. Okay? And the second condition is that given theta, P is a solution to the dynamic programming problem. And that means that given theta, we have that this condition holds. Okay? Then the NPL estimator was defined as a pair of theta and P where this is equals to 0 and this is equals to 0. Okay? Then let's see that this is exactly the first order conditions of optimality, the Lagrange condition in the single agent model. Okay? Well, in single agent model, what we have is the zero Jacobian property. The zero Jacobian property means that means that this derivative of Q with respect to P, it depends only on the derivative of phi with respect to P. This is going to be 0. And this is the zero Jacobian property, means that this is equals to 0. Then ignoring these conditions, okay, these conditions are always 0 at a fixed point, okay? Not asymptotical in a solution of the dynamic programming problem, these conditions are 0. And therefore we can completely ignore it, okay? In a constrained maximum likelihood estimator that is trying to solve this super high dimensional problem and ignores the zero Jacobian property, is going to compute in this Jacobian multiple times and iterating here, is going to waste a lot of time by solving this huge dimensional problem, and especially this additional set of conditions where these conditions are always satisfied, okay, in a fixed point, okay? That is, it might not be satisfied in our search for the maximum likelihood estimate, but at the maximum likelihood estimate for sure, because the maximum likelihood estimate is a fixed point, that is at every value of P and theta that satisfy this condition always hold in the single agent model. Then we can, by establishing this condition, we know that this condition always holds, then we can completely ignore. That's one of the things that the NPL estimator is doing, completely ignoring this, okay? In the case of single agent, okay? Unfortunately, for dynamic games, we don't have the zero Jacobian property, okay? Or let me put it another way. Now, this Jacobian, the derivative of the vector of the best responses with the vector of choice probabilities, we can think that it's a Jacobian with different blocks, okay? We have the block of the response or the derivative of my choice probabilities as player 1 as a function of my own choice probabilities of player 1. We have the derivative, the Jacobian, the block for the Jacobian of the choice probabilities of player 1, the best responses, choice probabilities as a function of the choice probabilities of player 2, and that's other block, and so on. And this large Jacobian matrix is the construction of these multiple blocks. Then it's still true that taking as given the choice probabilities of the other player, the best response of player 1 as a function of his own choice probabilities satisfy the zero Jacobian property. That means that this large Jacobian, the blocks in the middle, let me say in the main diagonal, though this a block, a main diagonal of blocks, okay? All these blocks in the main diagonal are 0. But outside of the main diagonal, we have no zeros at all in general, okay? If player 2 changes the probability of being in a market, given some particular state, in general, in the best response, that is going to change the best response probabilities of any other player, basically at any other state, okay? Let me say, because that is going to be important for computation, other than this zero Jacobian in the middle, the rest of the probabilities in this large Jacobian matrices, in general, even in very simple models like this model of market entry and exit, they are not zeros, okay? We don't have, unfortunately, an sparse matrix here. not sparse at all. Okay. Okay. Then the maximum likelihood estimator is going to look for theta, p, and lambda that solve these equations. And because we don't have the zero Jacobian property, we have in some way, one way or the other, to calculate these Jacobians. And these Jacobians, remember, what we have in these best response, what we have in these best responses, we have these choice probabilities enter in these transition probabilities, enter in this inverse matrix. We have to calculate the derivative of this inverse matrix with respect to the choice probabilities of other players. No closed form expression, nothing like that. No sparse matrices. This is computationally demanding. Okay. Okay. And the calculation of these Jacobians, okay, this Jacobian in the process of maximum likelihood estimation is going to be costly. And in some sense, this is a statement that is kind of algorithm free, okay? Maximum likelihood estimation requires computing this Jacobian, okay? How many times? It will depend on the type of algorithm that we use, but it requires the computation of these Jacobians, okay? And this is computationally costly, okay? Okay. Then let's consider the nested pseudo likelihood estimation in this context, okay? Then the definition of the nested pseudo likelihood is exactly the same as in single agent. Okay, it's again a vector p and theta that satisfies two conditions. Given theta, given p, given the vector of choice probabilities, theta maximizes the pseudo likelihood function. Okay, and given theta, p is a fixed point. Okay. And these are the conditions that characterize the MPL estimator, or a root of the MPL estimator, and these are the conditions that characterize the a solution of the likelihood function. Let me say the maximum likelihood estimator. Okay, and we have this additional set of conditions that we are not using in the maximum likelihood estimator. Okay. Now, it has two implications. Definitely, now we are not going to have efficiency because the MPL estimator is not using the moment conditions in 3. We can see all these conditions as a set of moment conditions to obtain our estimator. Okay. Then the set of moment conditions in 3, the MPL estimator is not using these conditions at all. That necessarily, without the zero Jacobian property, that will imply a loss of efficiency, for sure, okay? Asymptotic efficiency. But look, we don't have, well, for the moment, I'm not talking about any algorithm at all, okay? But you can see that the definition of the MPL does not involve any Jacobian with respect to P, okay? And that's going to be the key feature that is going to be still in the case of games, though we don't have the zero Jacobian property, we don't need to calculate this Jacobian, okay? And then that is going to imply substantial computational savings relative to other methods, like MPEG or any other method for the maximum likelihood estimation that requires to calculate this Jacobian matrix, okay? The second comment is that, well, before we have that this, in the single agent model, we have that the moment conditions that characterize the MPL estimator were exactly the same as the moment conditions that characterize the maximum likelihood estimator. Now, that's not the case. How can we claim that this estimator is still consistent? Okay, well, our paper, the 2007 paper, contains a formal proof of this. But let me provide a simple intuition for this. Okay, why still these moment conditions are still valid moment conditions and give us a consistent estimator, and they are sufficient to identify the parameters. Well, the intuition is the following. Well, condition 1 is obvious, is the same in the two cases. Condition 2 is different, okay? But asymptotically, if the restrictions that we are imposing in a model, in the estimation in a model are correct, okay, and the solution is interior, the Lagrange multiplier of the restrictions that we impose converge in probabilities to 0, okay? Then this vector of lambdas, our estimator of the estimation of lambda in maximum likelihood estimation, they converge always to 0, which means that the second set of conditions that we have for maximum likelihood estimation, asymptotically, they are equivalent to the set of conditions that we consider for the nested pseudo likelihood estimation. Okay. And these conditions 1 and 2 MPL, in the case of game, they are still valid moment conditions for the estimation of this model. Okay. Of course, there is a loss of efficiency, of asymptotic efficiency relative to the maximum likelihood estimator. The argument here in the case of single agent is that we are getting the maximum likelihood estimator with a lower computational cost, but we are not losing efficiency at all. Here, there is a trade-off. Okay, there is loss of efficiency with the benefit of a lower computation, or at least the potential benefit. Okay. Now, so far, I have defined the MPL estimator as before as an algorithm-free estimator. It's just defined in terms of a P and theta that satisfy these conditions. And this is a consistent estimator. Okay. Then the question now, the obvious question is, how do we get this estimator? Okay, how to compute this estimator? And this is going to be the key issue here, no? The computation of this type of estimator. Okay. Then I'm going to present two algorithms here. I will start with the algorithm that we first proposed in our paper in Econometrica 2007. That is basically the same version that extended to the case of games of the MPL algorithm that we consider in our single agent paper. Okay. Then similarly as in the single agent paper, we start with a guess, an initial arbitrary vector of choice probability, not necessarily a consistent estimator, because this is a full solution method. Then we start with some initial P0 that contains the choice probabilities of every player for every action and every possible state. And then the same as we did with the single agent, we construct this set tilde. I'm assuming that we have this linear improbabilities utility function. We construct these set tildes using the evaluation operator. We construct the E tildes. This becomes data. We have a standard McFadden likelihood function. We maximize with respect to theta. That is a globally concave likelihood function. Okay. Computational cost in the construction of set tilde and E tilde. Okay. Because we have to invert this matrix, large dimensional valuation matrix, but given this set tilde and E tilde, the estimation of the maximization with respect to theta is as simple as McFadden's static logic model. Okay. And then, given the new theta and the old P, we use our estimated model to construct new estimate of the choice probability. And this is, again, as trivial as in McFadden's logic, once we have estimated our model, to get the fitted value of the multinomial or the conditional logic model. Okay. Given that we have the set tilde and E tilde that we have constructed for the estimation, and we have our estimator of theta, we plug in this estimator of theta in the logit equations, and we get fitted values, predicted choice probabilities for every possible value of the state values. As simple as that. Okay? The main computational cost comes from given a P, calculate these Z tildes and E tildes, okay, before we make the maximum likelihood estimation. Okay? It comes from this, let me say, policy iteration, one step of the policy iteration mapping. Okay? Given that, updating theta and then given theta updating P is as simple as in a static model. And we have a globally, with this type of model, a globally concave likelihood function. Okay? Then every iteration is, one iteration is very simple. The main issue here will be convergence. Okay? For similar reason, or perhaps for the subtly same reason as the policy iterations for the solution of a Markov perfect equilibrium does not necessarily converge, okay? Because we don't have a contraction. This algorithm does not necessarily converge, okay? And there are a good number of applications where this works nicely, and a good number of examples of people that have shown that this doesn't work nicely at all, okay? Where there is no convergence at all, okay? Then this is definitely an important issue of this algorithm. Now, let me emphasize that this is not an issue of the estimator. In principle, of course, if you don't find any algorithm that converges, it will be an issue of the estimator too. But in principle, it's an issue of this algorithm. Okay. In general, let me say that this is an issue of many other estimators that are equilibrium models where we don't have a contraction property of the equilibrium. Okay. In that sense, this is a similar type of problem. Okay. Then, in a recent paper with Matthew Marquardt, we propose an alternative algorithm to compute the nested pseudo likelihood. This is a paper recently, well, published in 2021 in Quantitative Economics. Yep.
Step 2 seems to be only picking out one of the methods.
No, because these are best responses. If you want, there is an implicit assumption in all these. I don't know if that's exactly what you're concerned, but there is an implicit assumption in this approach, or in the definition of the likelihood that I have defined, is that there are not multiple equilibria in the data. Okay, these two markets with the same value of X, they have the same equilibrium. Okay, and it's not that we have a model with multiple equilibria. Given a value of theta, the model does not give us unique predictions about the probability distribution of the endogenous variables, but we do not have multiple equilibria in the data. But perhaps that's not your concern. Notice that all what we are doing in the step 2 is best responding. Okay, and the best response function, we are best responding to the previous vector of choice probabilities using an updated version of the vector of structural parameters.
I thought you said you have multiple.
Will you have multiple equilibrium? No. The best response function, as you say, is a function.
It's a function, but it could be a function that could cross each other at times. So
Sure.
but maybe you're
No, there is this multiplicity of equilibria, but this is a well-defined function and therefore a well-defined iteration. Okay, I'm not sure if I understand your concern. Of course, that we are going to have, given theta, we are going to have multiple p's that solve the fixed point problem, definitely. But here we are, okay, we are not in a step 2, we are not iterating up to, okay. In a step 2, we are making just one iteration. No, we are making, given theta and given p, there is only one new p. Okay, let me go to perhaps to the expressions, okay, of the best response function, okay.
So if I understand, the equilibrium is the fixed point P from that P, and there's multiple P.
Basically, given P, okay, there is a unique matrix here of valuations. There is a unique vector of expected profits. There is unique here. There is a unique vector of values, okay? Let's fix how every player is going to behave now and in the future. Given that, we can calculate for every player what is the vector of values. That is a function, okay? That gives us this vector of values, okay? And now I take that as given and I best response. And this gives me the best response choice probabilities of player I. This is a function. That's what we are doing in that iteration. We are just best responding to some choice probabilities. That's a well-defined function. Of course, if we iterate in this procedure, we may converge to an equilibrium or not. Suppose that we do. If you start with some alternative vector of choice probabilities and you iterate, you may converge to a different equilibrium, okay? Okay, for given the same value of parameter theta, okay? But that's different than saying that the best response is a correspondent. No, in this model, the best response is not a correspondent. It's a function, okay? Good question. Yes, that's true. Let me put it another way. Multiplicity of equilibria may or may not, okay, make more likely the possibility that we can have local maximum of our criterion function, okay? But this is not a specific concern of nested pseudo likelihood that might happen perfectly also with maximum likelihood estimation. We have these conditions that define the maximum likelihood estimator. You start with P, okay? Some P and some theta and some lambda. You iterate in this in a procedure to find a root of these equations. Because the model has multiplicity of equilibria, it could be that is more likely that there are multiple roots of these likelihood equations, okay? Definitely. And then we should be concerned about, well, at the end, all this algorithm, what is given us is a local optimum, okay? And we should be concerned that we are looking for the global optimum, and with multiplicity of equilibria in the model, perhaps the number of local maxima is larger than with single equilibrium. Definitely, that's perfectly possible. Yeah. You're welcome. Okay, then let me provide some yes, please. Excellent question. Yes, it is. Okay. At the end, the key condition for convergence of this of this algorithm is that the Jacobian matrix, okay, the spectral radius of the Jacobian matrix of theta with respect to P is in the unit interval, okay? Now the problem, and that's something that we study in my paper with Matthew in quantitative economics, is that even if you have a model that at the population level is stable, this spectral radius, that is the value, the maximum eigenvalue of this Jacobian matrix, this spectral radius is a random variable given a sample. Then even if at the population, this spectral radius is smaller than 1, and you have that the DGP, the data, the population has been generated with an stable equilibrium, there is always a strictly positive probability that in a sample, there are always samples where this spectral radius will be larger than 1. And what matters for the convergence of the algorithm is the spectral radius in a given sample, okay? Then even at the population level, you have this stability condition. Perhaps we are willing to assume that only stable equilibrium survive in the real world, okay? Even if that were the case, even if that were true, there are always samples, okay, where this condition is not going to hold, okay? And therefore your algorithm will not converge, okay? Okay. Then instead of using a instead of using a fixed point algorithm, basically our MPL algorithm is a fixed point algorithm. Okay, we are finding the fixed point of a particular operator. Notice that basically what we are going is from choice probabilities in one iteration of the MPL algorithm, we are going to choice probabilities to choice probabilities. We start with an initial choice probabilities, we obtain a new theta, but given the new theta, we obtain now a new P, okay? Then what we are looking is, what we have is a mapping, what we call the MPL mapping, that is the composition of the mapping C, the best response mapping, and the mapping theta hat, that is basically the pseudo likelihood estimator of theta for a given P. Then this composed mapping, that is the MPL mapping, is, okay, this algorithm is basically iterating in fixed point iterations in the MPL mapping, okay? And fixed point iterations converge typically when we have contraction properties, but generally do not converge when we don't have, or may not converge when we don't have, they are not guaranteed to converge when we don't have contraction property, okay? Then what if instead of looking at a fixed point iteration mapping, we consider this problem, we can consider the MPL estimator as solving a system of nonlinear equations, okay? In P, okay? Let me describe it. We have that the MPL estimator can be described as a P such that P is equals to F of P, okay? Where this function F is this MPL mapping, that is the composition of these two mappings that defines an iteration, okay? Then the MPL algorithm is basically iterating in this F fixed point mapping, and this might not converge. What if instead of looking at a solution in this way, or MPL estimator in this way, we say, let's define the function G of P as P minus F of P, okay? And what we are looking is for a solution, a value of P that makes G of P equals to 0. That's what we are looking for, okay? A solution to a system of nonlinear equations, okay? And then let's use algorithm for the solution of nonlinear equations, okay? And a natural choice will be Newton method, okay? We have a system of nonlinear equations, G of P equals to 0. What is a fantastic algorithm in terms of convergence properties? Newton's, Newton method is the best you can get in terms of convergence. Quadratic convergence is guaranteed. That's great. Okay. What is the problem with Newton's method? Okay. The problem with Newton's method is that the implementation of Newton's method will involve calculating the Jacobian of this. And that will imply calculating, okay, basically that's what I mean. Let's look at this mapping phi of P. Let's look at solution of a zero of this mapping. The problem is that the Newton method is going to, it requires derivative of the Jacobian of this phi of P with respect to P. But that involves the Jacobian of the psi with respect to P, and that's exactly what we want to avoid. That's the reason why we didn't want to use the maximum likelihood estimator, because we want to avoid the computation, or at least the repeated computation of this Jacobian matrix. Though that is the trade-off, basically. We could avoid, we could get convergence without any problem if we compute the NPL estimator by using Newton method in this system of nonlinear equations. The problem is that it's going to be as computationally costly of the same order of magnitude as maximum likelihood estimator, because it requires the repeated computation of this Jacobian. Okay. Then instead we use a class of algorithms that are called the spectral residual or spectral algorithm. That was first proposed by Shelley and Borwein in 1988, and in computational science, they have been developed very much, have applied successfully to many problems. High dimension, basically the idea is solving high dimension system of nonlinear equations. And the best type of method to solve high dimension system of nonlinear equations. What are the main advantage of this algorithm? Okay, is that they are derivative free. We don't have to calculate any Jacobian at all. Okay. Okay, and they have good convergence properties. Not as good as Newton. Okay, no free lunches, but they have much better convergence properties than fixed point iterations. Okay. Then this is a particular example. There are different versions of the spectral radius. Okay, basically, we can think in the Newton iteration as this type of expression here. Okay, where we have here lambda, this parameter, this scalar lambda. Instead of this scalar lambda, what we will have is the inverse of the Jacobian matrix of the mapping. Okay, then basically what the spectral radius algorithms are doing is replacing this Jacobian matrix by a scalar. That a scalar that we don't need to take any derivative to calculate that scalar, but a scalar that is updated at each iteration in such a way that it has the property that is upon convergence is going to converge to the spectral radius of the Jacobian matrix. Okay, that the Newton method will use. Okay, and then, well, that's the reason why it has good convergence properties. Okay. Then we have applied this to different dynamic games, and it was beautiful. It converged almost all the time. Okay, not all the time, but almost all the time after many Monte Carlo simulations and different representations of the model. You have all the Monte Carlo exercises in our paper and in our web page associated to that paper. Then, of course, this is still an open question of how to. The estimation of dynamic games is something very complicated, and of course this plenty of room to much improvement, not only in this estimator, but in the different alternative methods that have been proposed. Okay. Yep. Exactly. If alpha is constant and is equal to that, that's what we will have. Okay, and it's a part. Yeah, that will be a particular case, no. But in general, alpha is not going to be equals to 1 in this expression. Okay, alpha is updated at each iteration using this expression. This is one particular version. Okay, and there are also versions where there is there are extension. In fact, what we have used is this Lacruz, Martinez, and Radian, where at each iteration there is also a very simple line search optimization. Okay, but this is the key idea. Yeah. There are also versions where instead of a scalar here, you have a matrix, but a smaller, relatively simple matrix, like a diagonal matrix or things like that. That can improve the convergence properties with some additional computational costs. Okay, and there are different versions of MATLAB. Has the B solver of MATLAB is a particular version of a spectral residual method. We try in this paper, is not the ideal, okay? It's not, it doesn't work as well as but it definitely converges much better than fixed point iterations, okay? Just using the. What do you mean by the choice of the step? Here in this definition of the algorithm, the step is you don't have any choice for the step. The step is updated at each iteration according to this formula. There are different formulas, definitely, okay, for the updating of the steps, and yeah, there are trade-offs there. Yeah. Other questions? Yes. Have you treated, sorry?
How do you trade beta, the discount factor?
Excellent question. In the two approaches that I have described here, in the single agent and in the dynamic games, beta is fixed. Beta is not estimated. And this would not be a trivial extension at all for this type of method. I think that the simplicity of the, let me call it the inner algorithm, the simplicity of this step one is to some extent because we are not estimating beta, okay? Because we are taking beta as given. Otherwise, it will be substantially more complicated. And this is similarly as the linearity of the payoff function, having a payoff function or utility function that is linear in parameter. That's key for the computational good properties of this type of method. The same in terms of assuming that beta is known to the researcher. Because you could always do this MPL estimation for a grid of values for beta and then choose the, okay, but that requires additional estimation. But trying to estimate beta together with theta using MPL is not going to work well. You are going to lose all the computational advantages of the MPL in that case. Yeah. Other questions? Okay, that's it.